Hey everybody, it's Mr. N, and we are going to do some limits today at infinity and horizontal asymptotes. This is the 4-4 lesson from Stuart Calculus. Let's get right into it. All right, first of all, we have this definition. Let f be a function defined on some interval from a to infinity, then the limit as x goes to infinity of f of x equals L. This means that the values of f of x can be made arbitrarily close to L, the limit, by taking x sufficiently large. So at infinity, as I move on to infinity, making x super large, it is approaching this L value right here. This is, often we see it as an asymptote, but it's going to be known as our limit. And here's why. Because here's the asymptote, if you wanted to call it that, but really it's a limit because on this function, notice how the oscillation is getting smaller and smaller, so it's really crossing if you called it an asymptote. And it's crossing it, and it's coming through, and it's approaching this limiting value. All right, here's the second definition. Let f be a function defined on some interval from negative infinity to a, then the limit as x goes to negative infinity of f of x equals L. This means that f of x can be made arbitrarily close to L by taking x sufficiently large negative. So now we're just going to go in the other direction. All right, then we have the definition of a horizontal asymptote, and the line y equals L is called a horizontal asymptote of the curve y equals f of x if either the limit from x goes to infinity equals L, or the limit as x goes to negative infinity equals L. So hey, look at this, horizontal asymptote. So that's really what the limit is for the horizontal asymptote. And notice, if we said this was the horizontal asymptote, either way you wanted to think about it, it's still crossing it at this through this function right there. So it crosses an asymptote. Just want to point that out. Over here, if r is greater than 0 is a rational number, then the limit as x goes to infinity of 1 over x to the r is 0. If r is greater than 0, the rational number such that x to the r is defined for all x, then the limit as x goes to negative infinity of x to the r, 1 over x to the r power, is 0. So basically, it's what we've talked about before. If you have 1 over a very big number, right, you're going to get close to 0. If you have 1 over a very small number, that one's a little bit different. That one goes to infinity. So we've talked about these two. And it doesn't matter if your number here is a very, very large negative big number. Okay, that'll still go to 0. So the definition over here, restated precisely, remember we did this in a previous section, we talked about this, where f is a function on some interval a to infinity, the limit as x goes to negative infinity equals f of xl. This means for every epsilon, we got that back now, greater than 0, there's a corresponding number n such that if x is greater than n, then the absolute value of f of x minus L is less than epsilon. Of course, Stuart does show this graphically on page 238. You can look in that, and that's in, I believe, the version 6 that we're using, and they're on like version 8 or 9 now. And here it is again with the negative infinity. For every epsilon greater than 0, there is a corresponding number n, such that if x is less than n, then the absolute value of f of x minus L is less than epsilon. All right, moving on here. At infinity, let f be a function defined on some interval a to infinity, then the limit as x approaches infinity, f of x equals infinity. For every positive number m, there is a corresponding positive number n, such that if x is greater than n, then f of x is greater than m. This right here, we often call it end behavior. So we're looking at the end behavior, and you guys know how to do that. And we say as x goes to infinity, right, f of x does what? As x goes to negative infinity, f of x does what? So that's our end behavior for those. So the majority of this lesson, we've talked about limits, we've done limits, but we're going to go ahead and practice some of these limits at infinity and do this with the methods and techniques that we have already talked about in class. On number 1, okay, taking a look at this example. Now, there are a couple different ways. Let me remind you, often in trig, you guys are told to divide by the highest power in the denominator. And in this case, it would be x squared. So you would say everything over x squared like this. This is the first method that you're taught on how to do these, right? 5x squared over x squared plus 4x over x squared minus 1 over x squared. And then you're told that, okay, well, these will all go to 0 because of the definition that we had covered before, where 1 over a very big number, right, goes to 0. So that's how those will end up. Over here, these will reduce out, and you end up with 3/5 as the answer for the limit. Now, I told you guys there is a shortcut to this. You just take a look at the highest power. If the highest powers are the same, you take a look at the coefficients. If they match, that's your answer. There's actually the trig way of doing it, which is our algebra 2 way, which I think is much easier on these. And that's the one where if you have ax to the m over bx to the n, and you're looking at the highest power and the coefficients. If m is greater than n, that means the highest power on the top is bigger than the lowest power on the bottom. Then there is no horizontal asymptote. Okay, the limit in this case, there would be no limit. It would be infinite. If m equaled n, then a over b is your horizontal asymptote, which is going to be our limit. And if m is less than n, then y equals 0 is the horizontal asymptote, which would be our limit. All right, so let's take a look at number 2. So this is how we first teach it in Algebra 2. And I think it's a little bit more effective on these. It's just easier for you guys to remember and do. So over here, the coefficients match. So at infinity, my limit is going to be 4 over 2, which is 2, and that's my limit. All right, taking a look at the next one. On number 4. Well, I have to do a little something different with this, but you can see it's almost kind of the same. So let me explain to you. If you were to do it the other method, you would be dividing the top and bottom by 3 over, or I'm sorry, in this case it would be 3x over the square root of x squared, right? Plus the 4 over the square root of x squared, etc. Well, you don't really need to do that because we can recognize, because we're just looking at the highest powers. On the top I got a 3x, on the bottom I got a root 2 x squared like that. That would give me 3x over root 2 times the x if I separate it out, which would go away. So my limit, as x goes to infinity for this one, would be 3 over the square root of 2. That is, again, a shortcut method. And take a look at the next one. The next one is extremely similar, but yet a little bit different. Look at where I'm going. I'm going to negative infinity at this point. So if I do the same exact method, this time the limit as x goes to negative infinity, I'm plugging in a negative value. I will get this same sort of process where I have 3 times this negative, right? Because that's a negative x over here. I'm putting in negative x values. And then over here, 2x squared. But what happens when I put in a negative in there? Again, this is like doing that the shortcut way. And I'll show you the long way again in a second right here. If I square a negative, it's going to come out and it's going to be just fine. So I'll end up with this negative 3x on top, but on the bottom I'll have root 2, but that negative and times the negative became that positive, so I'll just have the x. Those will reduce out. I'll end up with negative 3 over root 2 in this case. Okay, so if we did this the long way, take a look. I have the limit as x goes to negative infinity, and I'm going to divide everything by that square root of x squared like I did over here. So it'd be 3x over root x squared plus 4 over root x squared all over the over here root 2x squared minus 5, and each of these over that x squared. Okay, so this top part becomes 3x, and now this is where the negative comes into play. If you put a negative in here, you're going to end up with negative 3x, but on the bottom, if you put a negative in here, you're just going to end up with a positive x. Over here, it doesn't matter because that goes to 0. On the bottom part of it over here, remember, you're putting in a negative in here and a negative in there. So on this part, if we break it up into the root 2x over x squared like that, minus the 5 over x squared like this part doesn't matter. This part, since they're both negatives, they'll be the same. You'll end up with just this root 2. On the top, the negative, we've already taken that into account, so that's where you end up with the negative 3 over root 2. All right, on the next one, take a look. If you try that same method, you will end up with the top with being, if you divide it out, the highest, right? And here you'll end up, those will go away, this will go to 0, you'll end up with just an x, and as you put infinity, there is no limit. As far as a number, the limit of x at infinity would be infinity. It's an infinite limit in this case. Now, if you took a look at it here, the way I told you with these shortcuts right here, this was the situation where you had your m is larger than n, so there's no horizontal asymptote, so the limit is infinite. Okay, that's that situation right there. And finally, find the horizontal asymptote, not fro, but for. Let's fix that. It's not a, this should be 4, f of x equals that. Well, we can do it the long way again, where we're going to take x over root x squared over root x squared plus 1 over root, or this would be x squared like that. Or you can just take it like the shortcut, and we know that as the limit, as x goes to infinity over here, I'm going to end up with the square root of x squared, which is just x over x, which is 1. Now, will this change? This is one of the horizontal asymptotes, so y equals 1 is a horizontal asymptote. Now, what if I went to negative infinity? What if we said the limit as x goes to negative infinity? In this case, the top will be negative x, and the bottom will stay as an x. So we'll get negative 1. So we can conclude that y equals negative 1 is also a horizontal asymptote of this. So we've got 2. So we had to take into account, since they're finding the horizontal asymptotes here, we had to take the account as it goes to infinity and as it goes to negative infinity to see what happens. In fact, if you graph this, you will get this function if you graph this, and it looks like this. It will go whoop. So here's one of the asymptotes, there's the other asymptotes. This is at 1, this is at negative 1. All right, and that's it. So thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.